Welcome everyone! This is the first video of Chapter 7 in the Crystal Clear Electronics 2 series. In this chapter, we will cover the in and outputs of the microcontroller, review some communication options, and discuss the relationship between the analog and digital world. These will be discussed in more detail later, but we believe it is important to have an overall picture.
This chapter would not be complete without the usual hands-on section. In this video, we will show you how to set up the in and outputs of the microcontroller. Later on, you can use this knowledge as a solid foundation to build upon when developing new applications.
We hope to share some useful insights with you and that you enjoy the video.
The 7th chapter was written by István Kristóf Csököly and revised by Ádám Szabó.
Today's main presenter is József Domonkos, who is a teacher at the Sapiencia Hungarian University of Transylvania. He came straight from Marosvásárhely, where he is the leader of the Crystal Clear Electronics workshop at the Bolyai Farkas High School.
Thank you for the introduction. Indeed, for many years now, even before the creation of the Crystal Clear Electronics series, we have been running electronics workshops at the Bolyai High School. Back then in the 90s, I also attended these workshops, and that's where I fell in love with electronics. This shaped my entire life path. I earned my university degree in electronics and telecommunications in Kolozsvár, and to this day, I teach electronics at Sapiencia University. I would also like to introduce my co-presenter. His name is Daniel Pivko. Dani, please share a few important things about yourself.
I don't want to make the introduction too long, as we've already met in several videos, including the previous one, Chapter 6. I am currently pursuing my master's degree at the Budapest University of Technology and Economics. Let's not waste more time and dive into the chapter. So now that we're settled, could you start by explaining exactly what we mean by the term pin on an electronic device, in this case the microcontroller?
Sure, let's get started. The pins of a microcontroller are the points where the inside of the device can make contact with the outside. From inside the controller, we can access the signals we need by means of metallized outputs, also known as pins. These outlets have a dual function. On one hand, they are used to establish the electrical connection. On the other hand, they secure the chip physically because the pins are soldered onto the circuit board. Nowadays, the same controller is available in several different packages, and different manufacturers use different leads for different packages.
Without being exhaustive, here are the most commonly used solutions. Let's start with DIP, or Dual Inline Package.
In this type of packaging, the outlets are placed on two, usually the longer sides of the device. This is the most common solution for through-hole applications. If you recall, the Atmega microcontroller used in Crystal Clear Electronics 1 had this type of packaging. The next one is the QFP, or the Quad Flat Package. In this case, the outlets are placed on all four sides of the device. This is commonly used in surface mount applications. Compared to the DIP package, the pins are much closer to each other. On the next figure, you can see the QFN, or Quad Flat No Lead packaging. This package is similar to the QFP, except that instead of pins, the edges and bottom of the package have pads. And lastly, the BGA, which stands for Broad Grid Array. In this case, the bottom of the device has a rectangular grid of small pads, which are pre-tinned by the manufacturer. The name of the package comes from these tin balls. On this figure, you can see the top and bottom view of the package.
Nowadays, a more powerful microcontroller capable of performing many functions can connect to the outside with many pins. At first glance, it is not an easy task to decide exactly which pin performs which function. In the following, I will describe the types of legs and their physical design using the STM32F446 microcontroller from ST Microelectronics. We'll also be using this device in later chapters.
Our STM32F446 microcontroller is designed with LQFP144 packaging, which stands for Low Profile Quad Flat Package, where 144 represents the number of legs. There are 36 legs on each side of the device, which gives us 4 times 36, totaling 144 pins. Among the pins essential for operation, The power pins are the most commonly used. They can be divided into two categories. The first group includes the following: VSS, VSSA, VEE, GND, and AGND. These legs are usually connected to the ground potential of the circuit. The role of the ground potential in the circuit is to set all other voltage levels relative to it, so that this level can be taken as zero. The second group includes the VDD, VDDA, VBAT, VCC, and VIN. A supply voltage corresponding to the range specified in the datasheet of the component is connected to these pins. The VREF plus and AREF legs on the controller can be connected to the reference voltage. This voltage can be generated in several ways: by connecting the supply voltage, by conditioning the supply voltage, or by a dedicated unit.
The microcontroller uses these voltages as a reference for the analog to digital converter, the ADC, and the digital to analog converter, the DAC periphery. You can learn about these converters in detail in chapters 11 and 12.
All microcontrollers need a clock signal to execute the program. There are controllers that use an internal or external clock, and there are also solutions where the microcontroller is designed to choose between both options. If the controller has dedicated legs for the external clock, you are able to connect a crystal oscillator or other external clock source to provide the clock signal that is essential for the operation of the microcontroller. On the STM32F446 controller, these are the PH0 and PH1 legs, which are used exclusively for connecting the crystal oscillator. If we use an external clock source, we need to connect it to the PH0 pin. The same goes for the Nucleo board as well. The 8 MHz signal generated by the ST-Link is connected to this pin.
The reset leg is used to reset the controller without removing the power supply. Usually a low-level logic signal of a given length is needed to be connected to reset the controller. On our development board, this leg is connected to a push button in order to allow the user to easily restart the running program.
If you already have a microcontroller and you want to control something, you have to load the program into its memory. In this chapter, we do this with the help of the SWD or Serial Wire Debug Interface. We use dedicated pins for this. P14 is designated as sys JTCK SWCLK. This is the clock signal. The PA13 pin is sys_JTMS #SWDIO. This is the data input and output pin. And lastly, PB03 is sys_JTD #SWO, an optional signal through which the microcontroller can send data during debugging.
A microcontroller's general purpose input and output pins are very commonly used and essential. These pins are labeled with the abbreviation GPIO, which stands for General Purpose Input/Output. These pins can be configured as logical inputs and outputs that can be set and read from our program, as well as special functions, for example analog inputs and outputs, communication interfaces or timers, just to name a few. The legs on the controller are arranged in groups called ports. On our microcontroller, these go from PA to PG, where the P stands for port. Each of these ports has a register associated with it, so that when programming, the leg can be referred to by the corresponding bit of the port register.
Some GPIO legs can be configured to generate an interrupt in the controller in case of a rising or falling edge, or low or high logic level of various events. These are the hardware interrupt legs. You can read more about program interrupts in the immediate events in the software interrupts chapter of the Crystal Clear Electronics. The essence of an interrupt is that some event causes the program to stop running. Then, the interrupt handler function, implemented in software, is executed for the interrupt. The controller then returns to the execution of the interrupted program where the interrupt happened. Some controllers, such as the STM32F446 series that we use, have an analog to digital converter, or ADC. This allows you to accurately measure voltage signals that not only have two logic states, low and high, but can also take any voltage value within a given range. If you want to measure a different signal, such as pressure or temperature, you first need to convert it to a voltage using some external circuit, which you can then measure with the ADC. On the left side of this diagram, there is a continuous analog voltage signal at the ADC input. The ADC output, on the other hand, is a sequence of binary numbers.
We'll cover this peripheral in more detail in Chapter 11, where we'll also demonstrate it with an example program.
As with ADCs, the use of digital to analog converters, or DACs, is also common. On a given pin, an output voltage signal can be generated, which can have a number of different signal levels, up to 256, 1024, 4096, or even more. The diagram shows that if we input binary formatted samples into the DAC, after filtering, we can obtain a continuous analog signal at the output.
The ADC and DAC peripherals will be discussed in more detail in later chapters of the curriculum, for example in Chapter 12.
With hardware support, and thus high precision, some outputs can be used to generate a square waveform with adjustable period time and duty cycle, also known as pulse width. The pulse width modulation, or PWM signal, is often used to control various processes, especially in electric motors. The following diagram shows signals with different pulse widths. The first has a 20%, the second 40%, the third 80%, and the fourth signal has a 100% duty cycle. The duty cycle is expressed as a percentage and indicates the ratio between the time spent at a high voltage level and the total period of the signal.
It's okay if you don't yet understand how ADC, DAC, and PWM work. These and the upcoming communication ports will be explained in detail in later chapters. Next, I go over some communication options, covering just a few examples rather than a complete list. Some legs can also perform specific communication functions if the peripheral is configured properly. The first one I'd like to mention is the UART, or Universal Asynchronous Receiver/Transmitter. This unit is responsible for managing asynchronous communications, usually inside the controller. UART is available on several legs. For example, UART TX can be found on PG14, and UART RX can be found on PG9 on the development board. These are mostly connected to hardware interrupts, so that the processor can be easily notified when new data is received.
As you can see here, the communication starts with a start bit, followed by data bits, then parity bits, and finally, one or more stop bits to terminate the communication. If a bit error occurs during the communication, this can be detected by the parity bit in a lucky case.
Most microcontrollers have dedicated modules for the commonly used synchronous serial communications, such as SPI or I2C.
Indeed, the SPI, or Serial Peripheral Interface Communication, is most commonly used within embedded systems between devices located within a short distance of each other, mostly using a master-slave structure. It is a subordinate connection where devices can have two roles, master and slave. As you can see on the diagram, multiple slaves can be connected to a master, which controls the timing and direction of the data flow. All communication over the SPI is controlled by the master. There is a dedicated wire for sending and receiving data. These are MOSI for master output, slave input, and MISO for master input, slave output. There's also a line for the clock called SCK for serial clock. Finally, each slave has its own enable signal referred to as SS, meaning slave select, or in some cases CS, the chip select. From the perspective of the master device, the roles of the 4 lines are as follows. In the case of MOSI, the data sent by the master to the slave is placed on this line. MISO contains the data sent by the slave to the master. SCK, or serial clock, is the clock signal. And with the slave select or chip select signal, the master selects which slave device it wants to communicate with. When handling multiple slave devices, multiple slave select or chip select signals are needed, as shown in the diagram.
The second module used for synchronous communication is I2C. The I2C, sometimes also known as IIC, whose acronyms come from Inter-Integrated Circuit, is a communication method that allows the creation of a multi-master, multi-slave structure. It is typically used for low-speed and short-distance communication between onboard systems.
In all cases, a master initiates the data transfer, but here only 2 wires are used for the communication. As you can see on the graph, on one wire, the master provides the clock signal, and on the other, the input and output data flows. This is the SDA, or serial data. The slaves have a unique ID, called device ID, which is used by the master to address to whom the message is addressed.
Now that we know how versatile these legs can be, let's look at how the circuitry inside the microcontroller is built.
Moving from the outside towards the inside of the controller, starting from the right edge of the picture, immediately after the I/O pin, the protection diodes are located inside the controller. These prevent the voltage from being too high, positive, or too low, or in other words, from becoming a negative voltage relative to ground potential. Next, you can see the output and input stages. On the graph, these are marked with dashed lines. If the pin is configured as an input driver, the output buffer or output data register is disabled. Meanwhile, the Schmitt trigger is enabled.
In electronics, the Schmitt trigger is a comparator circuit with hysteresis. We talked about it in great detail in chapter 14 of the Crystal Clear Electronics curriculum. It monitors the input voltage level and sets its output depending on it. When the voltage at the input reaches a certain level, the output switches to a high logic value. When the voltage at the input drops below a certain level, the output switches to a low logic value. Due to hysteresis, the 2 switching thresholds do not coincide. The Schmitt trigger here determines the logic voltage levels from which the controller takes the input as a high or a low logic value. Logic circuits detect a low, or 0, or high, or 1 logic value at their input and provide it at their output. In an ideal world, the low value would only include the 0 volt voltage level, while the high value would only include the supply voltage value, and the devices would never deviate from these values. Unfortunately, real life is a bit more complicated.
In reality, we rarely manage to achieve these ideal voltage values with logic signals. One of the reasons for this is that the transistors in our circuits are not ideal. They are not able to fully switch to the supply or to ground. To eliminate the problem of voltage level spread, the mapping of the input and output voltage ranges to logic levels were designed. On the input side, a voltage range from 0 to 0.8 volts was assigned to the low, 0 level, and from 2 to 5 volts to the high, 1 level. For output, the range from 0 to 0.5 volt represents the low signal level, and from 2.7 to 5 volts represent the high signal level. These values are given for TTL circuits, where TTL stands for transistor-transistor logic. The input of the Schmitt trigger has 2 resistors, which can be used to connect the input to a power supply or to ground. Such resistors are called pull-up and pull-down resistors. They are connected to the leg depending on the mode of operation you have set. There are two modes. In the case of pull-up mode, the upper resistor is connected between the supply voltage and the pin. The lower resistor is not connected, in which case the leg has a high logic value in the default state and an external device can pull it down to a low logic value. The other mode is the pull-down mode. In this case, the lower resistor is connected between the ground and the leg. The upper resistor is not connected. The leg shows a low logic value in the default state, and an external device can pull up to a high logic value. There is also a third mode, the high impedance or floating mode. In this case, neither the lower nor the upper resistor is connected to the pin. In the default state, the input has an undefined value and is set to float. In this case, the external device must be able to produce both the low and high logic values independently to operate as expected. The pull-up and pull-down resistors prevent inputs from floating and the resulting accidental switching.
When the leg is configured as an output, it will be able to drive a low or high logic value. If the application justifies it, pull-up and pull-down resistors can be used here as well. Next, we'll go through the output modes. The first is the push-pull mode.
Usually, this is the default configuration. The GPIO leg can act as both a push and a pull. When a low logic value is set on the output, the leg is connected to the ground potential via a field effect transistor, while when a high logic value is set, it is connected to the supply voltage via a FET. Thus, we can actively drive the output with both low and high logic levels.
The second option is the open drain or open collector mode.
Right. The term collector here refers to the collector of a bipolar junction transistor, while the drain refers to the drain of a field effect transistor. In this case, the output can only act as a sink. As you can see on the diagram, it has two states. The output is either at ground potential or in a high impedance state. With an external pull-up resistor, a high logic value can be achieved at the output. The advantage of this design is that no folding can occur when connecting multiple devices. That is a situation where one device forces a logic high on the line, while another device forces a logic low, which would result in a high current between the two devices, causing them to fail, cannot occur. This mode plays an important role, for example, in I2C bus communication, where the two lines, SDA and SCL, are provided with pull-up resistors.
Finally, let's also talk about the three-state or tri-state outputs.
Alright, the tri-state output combines the previous solutions. The output can be driven to a low or high logic value and to a high impedance state. Its most common use is to drive a bus. Only one of the tri-state output circuits connected to the bus line should be enabled at any one time. The outputs of the others are floating, so that they do not affect the bus state, nor do they damage each other.
With this, we've completed the overview of the theoretical concepts. Stay with us as the promised practical implementation is coming up in the next video. See you there!
See you!